Okay, we're going to look at an example here using what's called the binomial formula. And I've got a couple things that we'll just talk about. Here's an example. Let's say you have in a warehouse infinite supply of, well, not infinite, but practically infinite supply of well-mixed light bulbs. So in this factory, there are boxes and boxes and boxes of these things. And your job is to check the quality of the bulb. So you pull out a random sample of 4 bulbs, okay? And the engineers have told you that the probability that there's a bad bulb is 5 in 100. And that means that the probability of a good bulb is 95 out of 100. So this is the theoretical value. This is, well, they think it's the theoretical value, and maybe even by practice, they found this number to be true, okay? So you're wondering, okay, well, let's kind of give that a little test. Let's do a little test to see if that number appears to be right. Okay, so take a sample and ask yourself, what's the probability, if these numbers are right, assuming these are right, what's the probability I can get a sample, 4 bulb sample that has 3 defective bulbs in it, along with 1 good bulb? Okay, because let's just say that happens. Maybe somebody pulled a sample and 3 out of 4 bulbs were bad. You might be thinking, oh, how likely is that to happen if the bulbs are supposed to be only 5% bad and 95%? What's the likelihood that this would happen? Well, let's find out what it is. Let's see if this is realistic. So first thing we'll do is look at the number of ways that you could get 3 bad bulbs and 1 good bulb. In other words, a typical arrangement of that bulb sample might be first, second, third, fourth bulbs, like that. That could also have occurred first, second, third, fourth, like that. In other words, the good bulb could have been the 3rd bulb that was pulled out. So if you consider this the order in which the bulbs are pulled from the sample. And then this, or this, or this. So in other words, a 4 bulb sample, 1 of the bulbs is good, 3 are bad. And these are the 4 ways that could occur if you pulled a sample of 4 bulbs out, in which 3 were bad and 1 was good. So this could happen 4 different ways. Okay, now another way to view this is using our combination theory for counting. In a sense, when you look at these, you could view this as kind of like a word, and these are 4 words, and there is you wonder how many ways can I move that G around to make a different word, because moving the B's around, switching them with each other, doesn't make any difference. So if this were a word, then that G could go in 4 different places to create 4 different words. So in a sense, we're looking at combinations. We want to take four elements, 3 at a time, because we can look at the 3 bad bulbs and how to arrange them. These are the 4 ways we can do it. So that comes out to this. Or you could say, I want 4 bulbs and 1 of them's good. How many ways can I arrange that? It's the same question. And you get the same answer, 4. So what that tells you is that there are 4 ways that could have happened. That I could get 3 bad bulbs and 1 good bulb from any sample of 4 bulbs, period. These are the 4 things how it could have happened. So Now, we didn't even talk about probability yet. All we did was count the ways that this could have been done. So what we need to do, one way we could do is we could assign a probability to a single one of these occurring. And then we know that that can be done 4 different ways, so we would multiply it by 4. So now what we look at is the probability. Here it is. Okay, in other words, what's the probability of getting 3 bad bulbs and 1 good bulb? Well, 3 bad bulbs is first bad bulb times the second times the third. That's, see, this is probability. 3 bad bulbs, that's first, second, third bulb. We're multiplying the probabilities, each one of these. First, second, third. So here are the probabilities. We're going to multiply them. And then the fourth bulb would have to be a good bulb. And that probability is 0.95. So this gives us a probability of getting a single, on any single draw, 3 bad bulbs and 1 good bulb. And then we're going to multiply that by the 4 because we know that that could happen 4 different ways. In other words, this probability could occur, the same number would occur if I had any of the 4 samples here drawn out in this fashion, each one of these 4. So put these together and this is the number I get. Okay. Now in general, we could use this notation. Okay, and we'll talk about that in a minute, but okay, so this one, let's see. Okay, so here's my probability. So back to that original question. If somebody pulled out a sample and it was random from the, just went into the warehouse and picked a random box someplace in the pile and pulled out 4 bulbs, just kind of, or maybe just went around the whole warehouse and randomly selected 4 boxes and then pulled out 1 bulb from each of the boxes and then examined the bulbs and found out that 3 of them were bad and 1 of them was good. If these probabilities are to be believed, this one that we were given by the quality control people, then for something like this to happen would have this probability of occurring. In other words, if those numbers were true, those probabilities were true about the defectives and the good ones, then this is the probability that we would have gotten a sample like of that type. So that's kind of small. I mean, that's only, I mean, that's less than 1,000th. Okay, 1,000th, less than a 1/10% that would happen. So you might be suspect with these numbers. If you were the quality control people, you might be thinking, wait a minute, I mean, how could I get a sample this bad with those 3 bad bulbs if this is the probability that would happen? What are the chances that I would get that sample that I got with the 3 bad ones and the 1 good one? It doesn't look good. So this red flag would go up, and you might say, you know what, let's take another look at these numbers, and also maybe something's going on in production. Something isn't right. Maybe it's not production. Maybe it's in the packaging. Maybe it's in the store, in the warehouse. You know, why are there 3 bad bulbs in that selection? It doesn't seem like it should be that many. So that's a practical use for this sort of thing. And although we haven't gotten it down to a method, this whole idea that we're talking about here, quality control, QCA, quality control assurance. This could make somebody's job somewhere if he knew statistics. This is what they would do, things like that. Okay, so let's see. Um, okay, we're back. Let's see. Okay, so still no visitors today, but let's see. We're at about Wednesday. You see the timestamp here, 1:31. Okay. Um, let's see. Okay, so here's our question. And now, in general, we have a formula. We call it the binomial formula, and it looks like this. Uh, Q, X. Okay, so here's our binomial formula. And from that, let's see how it's used. From that last example that we talked about, we had, we called our success 3. So X was a 3, N was a 4 because we had a sample of 4, and we had a probability of a success was a 0.05, and Q was, it's 1 minus P, which is 0.95. And we use all these numbers, put them in here. So probability of getting that 3 successes in a sample of 4 with a probability of 0.05 for that success and a probability of 0.95 for failure. This is 4 minus 3. It's equal to this. And that was a 4, and that was a 0.05 to the third, and a 0.95 to the first power. And we saw that that was 0.000475. I believe that was, I think that was our number. Let me just check. I don't want to give you the wrong number there. Yeah, 3 zeros, 475. Okay, so that's how we used it in the last problem. Now, here's our next problem over here. Okay, so we'll assume that there are n trials. So n trials means, like in this case, n was 4. Each bulb that we pulled out was considered a trial. We could view it that way. And we had 4 trials, 4 bulbs. So here we have n is 66 trials, and probability 66, probability x equals 0, and 0 successes, and probability of a success is 0.5. So p equals 0.5, and that means that q would be also 0.5. It's 1 minus. See, that's 1 minus p. Okay. All right, so we're going to use our formula here. Probability of getting 0 successes for this trial, where we had 66 trials. Probability that we would have 0 successes in 66 trials, with a probability of success being 0.5 would be this now. So let's calculate this. Let's go through the 66, and then we have a 66 minus 0 factorial and a 0 factorial. And then 0.5 to the 0 is a 1. 0.5 to 66, well, I don't have to put that in my calculator. Okay, Now this over here just turns out to be a 1. Just 1 times 1 times 0.5 to the 66. So let's see what that happens. Okay, it's really tiny number. This is point. Well, I'm going to put it in scientific notation since it's so small. It's approximately 355,257 times 10 to the negative 20. Wow, that is small. Okay, so not likely for that to happen. Now, this context for this might be flipping a coin 66 times, because the probability for flipping a coin coming up heads is a half, coming up tails is a half. So success is heads, failure is tails. What is the probability that in 66 flips, you would have 0 heads and 66 tails? What's the probability that that would happen? This is it. And if you notice, it's really small. And that's an intuitive result. I think most people can relate to something like that. It's not likely to happen that you're going to never. I mean, you will never get ahead if you flip that coin 66 times. Most of us realize that that head's going to turn up, and probably long before 66 tries. But it is possible. There is a possibility that it might not turn up, and this is that possibility right here, that probability. Okay, so this probability might be it's very tiny, but similar probabilities are associated with lotteries, state lotteries, and people play that anyway. So this is very similar to that. Not quite this small, I would say, but probabilities that are very tiny, and people play the games anyway. So anyhow, um, let's see. So again, I said this could be thought of as a tail, flipping a coin and looking at how many times you would get 66 heads. What's the probability of getting 66 heads in that experiment? And so 66 trials, no heads at all. This is your probability. So when you look at it like that, it does have a context. And we could also do a similar problem. Let's try this. What do you think the probability would be if we had, there's 66 trials, let's say we want to get 33 heads. What's probability of getting 33 heads out of 66? This time we would have 66 choose 33 with a 0.5 to the 33 and a 0.5 to the 33. So I'm going to throw this in the calculator. I'm not going to mess with something like that. And I hope that my calculator will handle it, because there is a limit to some of these. I think factorial has a limit on the calculator. I think it might be 70, around 70, and then the number's too big for the calculator. 70 factorial, I think 71, maybe something like that. Now, some of the newer models might be able to hold more, but my old 83 plus, I think, is limited in that sense. But let's see. In fact, I'm gonna try something here before let's try. Let's check that. Okay, 70 factorial is too big. I might try. Let's try 69. Okay, it does work at 69 factorial. We will get it. So our numbers in here, I want to use the combination formula. So That's a 33. And I'm not even gonna try to write all this down. That's 0.5 to the 66 power, which is that last number that we had in the last problem, actually. 0.5 to the 66. It's that number down there with the 10 to the negative 20. Okay, this number comes out 0.097. Okay, so way bigger than this last number, but still, it's not that large. So probability is you would get half of those in heads and the other half in tails is actually only 0.097. Okay, so I think it's about all we're gonna do with this. So we'll just wrap it up.